the next speaker here. So final talk for this session, and then we'll take a short break. And it's the longest name at Eurocrypt, and I'm not going to try and say it. It's Mutu. Give it up for Mutu.
I'm going to talk about concurrent zero knowledge, simplifications and generalizations. This is joint work with Rafael and Dustin Tseng. I asked Kenny for some extra time to tell my name, but he said he wouldn't. So, as an order of first simplification, I'm going to introduce myself as Murthu. As all cryptography talks start, there's Alice, there's Bob, and they talk. But however, this is a theory talk, so I probably should start with saying, what is zero knowledge? And in zero knowledge, you have a prover and a verifier. And it says that for every verifier, there's a simulator. Did I say the verifier is malicious? Yeah. So for every malicious verifier with horns, there's a simulator S, such that every view in the real interaction can be generated by a simulator indistinguishably. Now, in the era of internet, everyone is not just concerned with standalone protocols, they want concurrent setting, so we're also going to be concerned about concurrent zero knowledge. So in concurrent zero knowledge, there's not just one verifier, but multiple verifiers. Now, what's known in this field? It's known, the best known black box protocol for this is, was given by, in a series of papers. The best known is the order login round protocol. This uses the simulation technique introduced by KP, that's Killian and Vietnam, and it was an analysis by PRS, that's Prabhakaran, Rosen, and Sahai. So we are going to be concerned about the simulation technique introduced by KP, which is a wonderful technique which is a static but oblivious remaining simulator. I'm not going to go into the details, but let me just tell you that it's static and oblivious because the remaining schedule does not depend on the session, and it only depends on the number of messages that's being exchanged between the verifier and the prover. You'll see more of this tomorrow in the talk precise concurrent zero knowledge, but let me just give what's a first simplification. For that, I should tell what the analysis by PRS for the KP simulator was. So the high-level idea is that they call a random tape on which a simulator fails as a bad random tape, and the one on which the simulator succeeds in generating a view as a good random tape. And the idea is that they show that they map one bad tape to 2 to the k distinct good tapes. And in this way, they show that the probability that the simulator fails is 1 over 2 to the k, and since k is ordered login, it's going to be negligible. But in their general approach, it's a bit complicated to show this mapping. So our first simplification here is that we show that we give a composable kind of proof where we map one bad unit to just 2 good units. And then we show that if you repeat this proof k times, you get 2 to the k good tapes, and that's why we get the failure to be 1 over 2 to the k. And finally, our generalization is that our proof works even for multi-round commitments as opposed to just 2-round commitments. And using this, we can use the instance-based commitments that was introduced by Ong and Madan, and we get the following results. We show that everything that has a zero-knowledge protocol can also have a concurrent zero-knowledge protocol, and this is an unconditional proof. So we show that if L has a statistical zero-knowledge proof, then it has an order login concurrent zero-knowledge proof. Then if it's further in NP, we can also show it for the others, for the statistical arguments, computational proofs, and computational arguments that you can also construct. You can also construct concurrent protocols. And thank you.